My topic for the day is artificial neural network modeling for slow pyrolysis process of biochar from banana peels and its effect on oxygen to carbon ratio. We all know that agricultural waste is an important issue not only for Malaysia, for the entire world. Banana being an important agricultural crop in Malaysia, it also generates a lot of agricultural waste in the form of banana peels. Banana peels have a lot of research interest, and one of the research interests being biochar, as it has a lot of application in terms of soil fertility and soil. How do we produce biochar? What is biochar? Biochar is a final product that's obtained because of the slow pyrolysis of biomass, which in this case is banana peels. How is this biochar produced? Biochar is produced by making use of banana peels and rinsing them with distilled water, which is torn into thin strips and then dried in an oven, followed by it's being ground in a rotor beater mill to make it into a fine particle of size of 1 to 2 millimeters. These fine particles are then subjected to slow pyrolysis process using a horizontal tube furnace, which can finally get us biochar. So the experiments that were conducted are using the RSM approach by varying the heating temperature, heating rate, and residence time. And the samples were then analyzed using FESEM to get the oxygen to carbon ratio values. So the objective of this research is to obtain a feed-forward neural network model for the slow pyrolysis process with heating temperature, heating rate, and residence time as the input and oxygen to carbon ratio as the output. What is artificial neural networks? Artificial neural networks is a AI modeling technique which has a structure which consists of inputs, hidden layer, and output layer. The input layer has the input nodes, hidden layer has the hidden nodes, and the output layer has the output. The inputs are the operating conditions of this pyrolysis process, and these operating conditions has fed us the information into the input layer, which are then processed into the hidden layer, where the hidden nodes make use of these information and processes them, and finally gives us the output, which is to predict the outputs. So in this case, oxygen to carbon ratio is the output, so the prediction would be to predict the experimental responses by making use of the transfer functions like hard limit, linear, and log sigmoid transfer functions. We also do the trial and error by using the hidden neurons. So the MATLAB software is used in this particular research to carry out the modeling. So the codes were developed, and the data that was obtained from the experiments were subjected to training, testing, and validation. 20 set of data were used in this particular modeling process. The 20 data were divided into 70% for training, 15% for testing, and 15% for validation. The performance of this model was determined by using two important criterions, namely determination coefficient R squared and mean squared error MS. 10 different training algorithms were used in this particular research, which are mentioned in the slides, and all these 10 training algorithms were used to determine the most suitable training algorithm that would give us the best results in terms of R square and MSE values. As far as the results go, uh, this result that you see on the screen is the ANN modeling results that are obtained from Levenberg-Marquardt training algorithm. The reason this particular training algorithm's results are being shown is because Levenberg-Marquardt training algorithm gave the best results among all the 10 training algorithms, and the results that you see is the R value, R squared value, mean squared error for the output, and the mean squared error for the validation data. So the results were obtained for 1 to 25 hidden neurons, and among all the 25 hidden neurons, the 24th hidden neuron gave the best results in terms of R squared and mean squared error value. This plot is once again a representation of the Levenberg-Marquardt training algorithm results, which provides us the results in terms of the lowest MSE value, because the lower the MSE values, the better is the model. Similarly, higher the R squared values, better is the model. So the R squared values that's shown in this particular figure shows that for a hidden neuron of 24, R squared value of 0.99858 is obtained as the R squared value, and lowest MSE value for validation and output data were obtained for the training algorithm Levenberg-Marquardt method of 0.04467 and 0.00001 respectively. So if we look at the table, this once again summarizes the ANN results for the various training algorithms, and for each training algorithm, the number of hidden neurons have been identified that give us the lowest training, testing, and validation results, the R squared values, and the output MSE and validation MSE values. So out of all these training algorithms, the final conclusion is that train LM is the best training algorithm that could give us the best results in terms of R squared, output MSE, and validation MSE. Once again, this graph shows the performance criterion for various training functions. So as I mentioned, the different training functions were tried out, and out of the different training algorithms, train LM gave us the best results in terms of R squared and values. And this shows the regression value. R is the regression, and this shows the regression results for the Levenberg-Marquardt method. Once again, Levenberg-Marquardt showed us. So the conclusion out of this research is that out of all the training algorithms that were tried, Levenberg-Marquardt training algorithm gave us the best results for the hidden neuron of 24 with the best R square value of 0.99858 and the lowest MSE value of 0.04467. Thanks for listening.